My name is Dr. Katanya Kuntz. I'm the founder and CEO of Qubo Consulting Corp, and this is our first webinar, part of our series. This one is focused on quantum communication for executives, the first mover's advantage. So again, like I said, welcome everyone. My background is experimental quantum physics. If you're not sure what that is, I have a picture coming up that will help solve that mystery. Qubo Consulting offers training and consulting for technical and non-technical audiences. And so if you're here today and you've never heard what a quantum computer is or quantum communication, that is okay. And like I said, I'm an experimental quantum physicist. This was one of the first optics experiments that I ever did. This was at the University of Calgary. Technically, this was a classical optics experiment versus quantum, but the technical details and equipment all look the same. So you see an optics table here with lots of holes in a grid pattern, and then you see some optics like lenses. There's a big glowing cube here. That's actually a big polarization beam splitter. And we have this laser coming out. It's very, very, very bright. And then you see this very narrow beam in the middle, and then all of a sudden it just disappears. The image just diffracts away. And so the whole point of this experiment was to create this very, very special beam that's called a Bessel beam, and it kind of looks like a lightsaber, so that's why I call it a lightsaber. So these are the types of experiments that I work on. I use lasers and optical devices to create what's called quantum states of light. And this can be used for quantum communication, also quantum sensing, quantum computing. So again, welcome everyone. I just want to remind you, please keep an open mind. Yes, we are going to talk about quantum physics today, but I promise you will understand everything if you just listen to how I explain it and ask lots of questions if anything is a mystery. And we also have, like I said, lots of people on the call from Qubo. We have Lorna, who has background also in teaching, and she's a non-quantum expert, and so she's on your side if you're a non-quantum expert too. So Lorna, did you want to say hi?
Hi, everybody. I'll be here to help support you guys. Again, I'll be doing the attendance. So just as Dr. Katanya has said, make sure that your name is the correct name. And as we go through this, there will be, if you have any questions, feel free to use the Q&A box and we can monitor that and make sure that your questions are answered. And like we said, feel free to ask lots of questions as we get through our seminar today.
Wonderful. Thank you, Lorna. All right. So an overview for today's talk. First, I'm going to present an introduction to quantum communication. We'll take a step back and we'll talk about first what is quantum in general, quantum technologies, what is a quantum computer, also some really important things like the quantum threat and Q-Day. And then I'll go into quantum communication and what is the quantum internet. So this will kind of lay the foundation, give us a common framework to discuss. Then we invite our guest speaker, Didier Guignard from VeriQloud. And so he'll be presenting all about their solutions for quantum communication, both for data in transit and in storage. And other cool things like blind quantum computing, which I'll also introduce to you before we bring him on the stage, on the virtual stage. And then I will go through another short presentation. We'll get a bit more into the use cases of quantum communication. So if you ever heard of entanglement, there's something called entanglement distribution. What is that? Why is it important? Why are these words important in our world of quantum? I'll talk about a real life use case, the Gotham Q quantum optical fiber network that's in the US. And then that's talking about terrestrial networks to start, like fiber optic networks on the ground. But if we want to connect users that are further apart, say different continents, we want to start doing ground to space communication. So I'll go through what is that, both using satellites and also things like high altitude platforms, HAPS. and finish up with some more use cases. What's the latest and greatest in quantum communication? And then we will bring on another guest speaker. We have Erik Guignard from Photonics Foundry. If you've been to a Qubo presentation before, you might have seen Erik present. And so we've got him back again with high demand. All right, so if there's any questions, like we said, please feel free to either raise your hand and unmute. We are recording the session, so if you don't want your voice and face recorded, then please turn off your video and sound. And if you can always write something into the chat instead. All right, so to get started, what is quantum communication? Well, first, let's take a step back. What is quantum? So quantum refers to quantum physics. This is also called quantum mechanics. That's the mathematics behind the physics of quantum physics. And this is all the study of the tiny. So the study of the smallest particles and energy that make up our universe. Things like atoms, ions, particles of light that we're going to talk about a lot today called photons. So this is all things that we can't see with our eye. Our eyes can see the macro world, the big world, and this is the micro world, the small world. So on this different scale, matter and energy just behave differently compared to our everyday life. And that's why we have this different mathematics to explain it. And so there's technologies that we already have in our everyday world that are based on the principles of quantum physics. Things like the transistor to let your computer work, the current internet that I'm using to talk with you, the electronics in this microphone. All these devices are operating on the principles of quantum physics, whether you knew it or not, but it's not actually part of this new revolution, this second revolution that's coming now that we're calling quantum 2.0. And so this quantum 2.0 technologies are things that are using individual particles like atoms, ions, photons, the spin, which is a quantum characteristic of a particle. You can use these qualities to now do the computation, the sensing, the communication. And so that's very different compared to our previous technologies. And before I get too far, I just want to make sure that the whole room knows AI is not quantum. Artificial intelligence is classical computers that are working together to solve a problem. This is not a quantum computer, and this has nothing to do with quantum. The energy when you're working on a traditional computer like we have right now, that I'm using right now, the energy, the information is being stored as a 0 or a 1. Whereas a quantum computer is very different. A quantum computer is using qubits, quantum bits, to store and process this information. These qubits are existing in a combination state or a superposition state of 0 and 1. And this is something that just doesn't happen in everyday life that you see. That's what Schrödinger was trying to show with this thought experiment. This is this cartoon here showing a dead/alive cat in a box. If you've ever heard of Schrödinger's cat, it was a thought experiment, a way to imagine what is this weird superposition that quantum particles and quantum devices can exist in, but our everyday world doesn't really do that. So in this thought experiment, you see there's like a vial of poison, and there's a hammer that's either breaking it or not breaking it. And the release of that hammer is probabilistic based off of some other, like in this case, a radioactive decay. So as time goes on, there's a higher and higher chance that the hammer will fall and the poison will break and the cat will die. But until you actually observe the cat, you don't know. And so that's why this is considered a big superposition state, and because it's an actual thing you can see with your own eyes. But for our quantum devices, like I said, we're using individual particles, the spin of an electron, a particle of light like a photon, also superconducting circuits, we'll hear about that, and NV centers, nitrogen vacancy centers. So these are all different platforms that can be used to make a quantum computer. But if you do an image search of what is a quantum computer, a lot of people will get a picture like this, even myself. You'll get 90% looking like that, and a lot of people think that that is a quantum computer. However, that is not the quantum computer. That is actually a cryogenic fridge to run one particular type of quantum computer. That's called a superconducting circuit, which is shown here, for example. So this huge chandelier, and some of the cryogenic fridges are now smaller, they are just to bring down the temperature to almost 0 degrees Kelvin. So 0 degrees Kelvin is absolute zero. It's the complete absence of any energy, temperature. Basically, our universe is at like 3.2 degrees Kelvin, roughly 2.8, much higher than 0.001 degrees Kelvin. But to get something to work as a superconducting circuit, you have to supercool it. And so they use liquid helium and vacuum pumps and things like this to bring down the temperature to allow this chip to get into a superconducting state, and then it acts as a qubit, and then now you have a quantum computer. So like I said, there's very special quantum properties that allow a quantum computer to potentially have significantly more power than our traditional classical computers. So quantum computers, for example, could solve problems faster, more efficiently, thanks to algorithms like Shor's algorithm and Grover's search. So Shor's algorithm is the one that could potentially hack our current public key encryption, and I'll talk about that in just a minute. And Grover's search is a very powerful database search. And so it's very hard for our traditional classical computers to do a database search or to find anomalies in data. But that's actually a problem that's very straightforward for a quantum computer to do. But keep in mind that quantum computers are not better at everything. And so there's going to be some operations that just won't make sense to run on a quantum computer versus a classical computer. And so most likely we wouldn't want to replace all of our classical computers with quantum computers. We probably want a hybrid system in the future. So I just want to see if anyone in the virtual audience, you can react in chat, or you could do a thumbs up or anything like that. Has anyone heard of the harvest now, decrypt later threat? Oh, I see a few thumbs up. That's awesome. Yeah, but not too many thumbs up. So this is why we're talking about this. Wonderful, wonderful. All right, so there's something called the quantum threat. So we already know currently that there are bad actors and adversaries who are harvesting your data that's encrypted, and maybe they can't break it right now, but they're storing it and then trying later when they do have a more sophisticated hacking device. Also, AI itself is becoming very, very good at hacking. I think there was a really big, was it Canvas? There was a very large hack that just happened and affected like 8,000 post-secondary schools or something. Yeah, Canvas. So we know that hacks are happening every day. And just to add to that, a quantum computer could potentially be able to hack some of our everyday public key encryption, like RSA encryption that we use for online banking, shopping, transactions, things like this. The day that a quantum computer is powerful enough to be able to hack that level of encryption is called Q-Day. And so we're predicting, as an industry, we're predicting this to be in the next 5 to 15 years. But this is not necessarily a linear thing happening. As our engineering and our abilities to make these devices get better and better, the number of qubits we make and the power of these devices are improving. So also, a lot of people's encryption methods take a while to replace. You can't just go to an organization and be like, okay, just swap out everything you're using now and for this other type of encryption. This is a slow process that will take mitigation and things like that over several years, sometimes even decades. So the fact that this is, we could have a powerful enough computer in the next 5 years should bring alarm to a lot of people's minds. However, there are quantum solutions to this quantum threat. There's something called quantum safe encryption. So there's post-quantum cryptography, or PQC. These are harder math problems that are supposed to be difficult for both a classical and quantum computer to be able to solve. And so it's not a fully, theoretically, 100% secure method of encryption. However, it is something that is better than nothing for sure. And it is what's called quantum safe. So again, protecting you against future quantum attacks. 100% theoretically secure form of encryption would be quantum key distribution. Once you've created your encryption key between your two parties, which we'll talk about in a minute, you then implement one-time pad encryption, and that is theoretically 100% secure. So like I said, quantum key distribution is a quantum solution that is theoretically 100% secure. It's the real-time generation of an encryption key between two parties. You see in this image here, we have a satellite and there's a ground station with a telescope talking to that satellite, connecting via the photons.
Katanya,
Yep.
there's a question in the chat. It says, is it Kyber? That's an example of QKD? QKD?
That might be one of the protocol names. Is it a there's a lot of different, there's like 30 different QKD protocols. So that could be one of the protocol names. I don't know, send me an email and I can verify. Thank you. Any other questions right now? No? Good. Okay. Thank you, Marco.
Oh, Rainier, I just answered here. Crystal Kyber is a PQC algorithm standardized by
Thank
NIST.
you, Reiner. Thank you. Yes, yes. Now with more context, I understand. Yeah, so there are PQC algorithms that, like Reiner said, has been standardized by NIST. So some of these algorithms, for example, they get published and then they can be quickly hacked. So it's not, like I said, theoretically 100% secure, but there are 3 or 4 that are still holding, I believe, NIST protocols that are being implemented now for PQC. Yes. Awesome. So for QKD, we have this real-time generation of an encryption key. So it's not the fact that Alice has a key and is sending the key to Bob. It's actually that Alice and Bob are generating this encryption key together. And so you see the little tiny particles with little arrows. So these is a graphical representation of single photons. And so Alice and Bob then can use this secret key that they've generated using single photons to generate and measure the key. And then they can implement one-time pad encryption, which is theoretically 100% secure as long as they do it correctly. Meaning the message and the key have to be the same length. They can only use the key once, and the key has to be completely random. And thanks to quantum physics, this process is completely random by nature. So this is why the security of QKD is based on physical processes that are not vulnerable to a quantum computer. So you know about the classical internet. We have lots of underwater cabling connecting all of our continents. And this length scale here in this heat map is showing from 0 to roughly 36 to 40,000 kilometers. And so you see in some regions of the Earth, we've got cabling that goes very, very far. And so we've also have like the internet in satellites, network. So we have different ways to transmit our classical data right now, whether it's through fiber optic cable, like these yellow cables that you see here, or via satellite, or there are free space internet connections as well for the classical internet. So now, what would be the quantum version of all of this? So the quantum internet is now connecting up quantum devices. So that would be quantum sensors, quantum computers, quantum communication systems, things like this. And so now you're sending quantum information via single photons or entangled photons. Entanglement just means there's a special correlation. There's a connection between these two particles, and you can harness that connection to do lots of different things. And in this case, for quantum communication, you can harness entangled photons to do very secure communication that cannot be hacked. But you don't have to have entanglement to do communication. You can also just use single photons. That's also secure. There's just an extra level of security if you use entanglement. But because you're transmitting single photons and it's quantum information, it's just a little different compared to our classical data that we transmit every day. So quantum information is very sensitive to loss and to noise in the environment. And what do I mean by loss? I mean energy that's being dissipated, that's being absorbed. So you see in this cartoon here, you have light that's coming into an optical fiber. It's bouncing around. Some of the light is going to be lost into the insulation around the fiber. You can see in this picture here, someone's exaggerating that loss by bending the fiber. You can see the light scattering. And so all of this loss is bad. And so now you have noise as well. So noise can affect the quantum state and cause it to become a classical state. And what do I mean by noise? Like literally a truck driving over a street will be rumbling the ground, and your underground network could be disturbed by that vibration. That's how sensitive these devices can be. So to send quantum information through long distances and things like this, we can't just turn up the power, and we can't use classical amplifiers. Does anybody know why? I'm gonna go with no. Okay, so the reason why is because we can't turn up the power. If we do that, we're going to turn our quantum state into a classical state. And so it's very, very bright, bright light. And we can't use amplifiers to boost the signal because amplifiers are basically like big cloning machines, copying machines. And in quantum physics, we have this thing called the no cloning theorem. And it means that we can't copy a quantum state. And that's actually really good. That's part of the security of quantum communication. A hacker can't just steal your photon, copy it without you knowing it, and then give it back to you. And so because of this, we have some distance limitations. And so if you want to send quantum information, quantum light, through fiber optic cable without any boosters, there are quantum versions of boosters like quantum repeaters, nonlinear amplifiers. These can also boost the signal longer distances. But if you just have dark fiber, no amplifiers, you have roughly 500 kilometers that you can send quantum information, roughly. The exact distance is protocol and situational dependent. And there are ways, like I said, to boost the signal that's allowed in the quantum world. You can do things like entanglement swapping. And this is a non-technical lecture, so I'm not going to go into this. If you have a question, I can totally answer it later. Also, we're going to stop the recording at the end, and we're going to open the floor for more discussion and Q&A, so we can always answer more technical questions at the end as well. And so you can transfer quantum information between these different quantum nodes in your network by using these repeaters, memories, things like this. However, they are still being developed. They're in the R&D stage. Some have been demonstrated experimentally for sure, but they're not ready to necessarily be deployed into space or in real time on the ground. So if you want to connect two users, like if you see in this image here, two different continents, then going through fiber just isn't feasible right now because of the repeater distance limitation. So you really want to go to space. And so this cartoon is showing all the different ways, different types of quantum links that you can have, whether it's from a ground station to a high altitude platform, which is this link number 1 showing an airplane, whether it's satellite to ground links or satellite to satellite links. A future quantum network, a future quantum internet will probably need all of these types of links. And ground to space quantum networks might sound like a science fiction, but they have been demonstrated, as I'll show you in the second lecture. And we do have quantum communication satellite missions happening right now, including Canada's that will be launching soon. All right, and so just to give you a taste of why we care about the quantum internet, why are we doing all this if it's hard to send photons through fiber and things like this? Because it's really important. If you want to have, for example, distributed quantum computing, this is connecting several different quantum computers together to work on a single problem, like what we do now with cloud computing and AI. You need a quantum network to connect those quantum computers. Also, like I said, blind quantum computing. This is where your quantum server is carrying out your client's computational requests, but it's blind. The server is blind. So all the data, the inputs, the outputs, and even the operations being performed all remain private. And it's unknown to the central quantum computer. For then quantum sensing, if we want to entangle and connect different quantum sensors, this has a lot of advantages. You can remove common background noise, and that significantly improves the measurement sensitivity. We talked about QKD. I'll talk more about that in the second lecture. But for now, if you want to connect Alice and Bob, your sender and receiver in QKD, that connection between them is a quantum network. Whether it's free space, fiber, satellite, that is a quantum network to connect up your devices. And then finally, quantum money. You might have heard of this before, I don't know. So this is quantum secured financial transactions. So now your bank and the user are sharing a quantum state. For example, a pair of entangled photons. One stays with the bank, one gets sent to you. It doesn't even have to be entanglement. It can also just be single photons. But in order to distribute that entanglement or distribute those single photons, you need a quantum network. So I hope I've convinced you of why we need the quantum internet and what is communication. I want to see if there's any other questions. I see in the chat we're good, I think.
Yeah, we're good. There's no questions
Okay.
so far. But want to encourage you guys to, or feel free also just to raise your hand if it's easier just to talk as we're going through.
Wonderful. All right, well then I'll get straight over to our guest speaker. Let's get some guest speaker music going. All right, so let's pretend I haven't been telling you who our guest speakers will be today. We have a tech founder coming to share about their company. Welcome, Didier. Has over 30 years professional experience spanning leadership roles in strategic planning, research and development, product management, and system analysis. Didier's background is a master's in computer science, and also a bachelor's degree in economics, and is part of VeriQloud. VeriQloud is the pioneer in quantum-safe cybersecurity. They deliver software and hardware solutions for cloud data storage, communication, and computation. So welcome, Didier. I see you there. I'll stop sharing.
All right. Hi, everybody. Thanks, Katanya, for inviting me in this great webinar. And hi, everybody. So I just going to share my screen. Hopefully it will work out. All right. Okay. All right. Well, I'm just going to introduce our co-owner or founder of VeriQloud and who we are. So VeriQloud actually is a company that was created in 2017, and the headquarter is based in Paris, France. As you can see, there were three co-founders. And I just wanted to highlight the fact that one of our co-founder, that is Dr. Elam Kashafi, is actually one of the co-author that created the first blind quantum computing protocol that Katanya just mentioned. So we have a lot of experience, history in this kind of security related between a client and a server where data are computed based on encryption data and not on clear data. So, and we are actually, we have subsidiaries here in Canada, and that's why I'm here and I'm representing VeriQloud here in Canada, based in Ottawa, actually. Hey, let's go. So basically, our DNA of VeriCloud is data protection. So basically, what we do, we develop a full stack of data protection solution. As Katanya mentioned at the beginning of the webinar, there is different, way of using data. So what we call data in transit, data at rest, and data in use. What it means that data in transit means that you send some data through the internet, for instance. So they are in transit from a location to a B location. Data at rest is where you store your data on your computer, on a cloud, wherever you want to store them. And data in use is basically when you use the data for doing some computation and get some results that you want to have. I mean, resolve some of your day-to-day activities or whatever request you have. So what we have done, we have developed actually different lines of product that covers this whole different categories of data: data in transit, at rest, and in use. And we have three major lines that are called Q-line, Casmat, and Shuffle slash and Q Enclave. So let's go a little bit deeper on these three different line of product that are either, as Katanya mentioned, PQC solution, meaning post-quantum cryptography solution. That means we're not using pure QKD technologies or devices, but we have developed protocol that we know today that are fully secure against classical and quantum attacks. As we have our solution, for example, Q-line and Q-enclave, as I will mention, I will present to you, that are using actually quantum technologies, like Katanya mentioned, QKD, for instance. Okay, let's go to Q-line, that is securing your data in transit. Q-line is actually our own QKD or quantum key distribution solution. So we develop and provide these devices that are actually a pair of devices where you have two people, person A and person B, they want to exchange a key and they want to make sure that this key is not hacked when they are distributed between A and B. So they are using this pair of devices. So one device is owned by person A and one device is owned by person B. And in between we have a network, basically an optical network, optical fiber network. So what we do actually with these devices is a bit different from other competitors or other company that you may have heard that are quite well known in this area, like ID Quantic from Switzerland that has just been bought by IonQ actually from United States of America, and Toshiba as well. They are, I think, the most leader in this industry. Anyway, what we are producing is actually an open source quantum key distribution, meaning that we work with clients that want to go beyond key distribution and they want to use the technologies of these devices to do other type of experiment, other type of application. And this is why we call open source, because the whole system, from the electronic part to the hardware to the photonic devices, can be replaced, can be customized for their own purpose or own application. And so we are actually mainly working with public institutions like universities that want to do some experiment, Here in Canada, we have quite a few customers in this area of public institution. We're also working with private company or telecommunication companies that want to um, actually be able to use their current classical network infrastructure and devices, but be able to transport quantum or qubits information. And in order to couple these two different worlds, they actually want to use QKD that they can tweak, they can open, they can combine with their system. And this is very interesting because I think what we're moving into is not just a pure quantum internet or pure quantum set of devices, but it will be, at least at the beginning, a combination of classical and quantum internet devices, network, and so on. So what we have been able to do with this open source QKD is here are some examples that we have done that go beyond just exchanging keys. So I won't go through all the different details, but what we have been, for instance, doing with Deutsche Telekom in their network facilities in Germany is we have been able to actually on a local area, I think was close to Hamburg, we have been able to create what we call a star architectures, where just with one pair of QKD device, we can actually create a set of communication between a lot of different users. So that simplifies the hardware part, and it actually mimics the same situation as the classical internet, where you have multiple, users that exchange information, that chat together as we do today via Zoom, right? We're like different people in different location, and this is what I would call a star architecture. And by applying what we have done in Germany, we could do the same here if we would be a bit closer, because as Katanya mentioned right now, quantum QKD is limited with the distance, that is a few hundred kilometers. But if we would be all around Hamburg, for instance, we could actually do this Zoom using QKD that will be very secure. So this is just one example that we do with this Q line for data in transit. Let's go with the next set of product we have is actually a product that is not pure QKD or using quantum technologies, but we have developed a protocol that is based on post-quantum cryptography, meaning that today we know that if a quantum computer would be available, we would be protected against his power. Why? Because actually this protocol is not based on the complexity of computation, as most of the classical algorithms today, like RSA, are based on complexity of mathematics behind. Is actually based on shares. So what we do, we take your data, we split the data into different shares, we apply a minimum of cryptography on it, and then you can throw these different shares in different nodes, meaning in different location. So basically you could say, okay, my data, one share of my data will go to Google. One of our share will go to my own server. One of our share will go on another public cloud. And by doing that, if somebody wants to hack your data, he has to be able to access Google. He has to be able to access your own server, and has to access the third cloud that you have put the third share. And that's becoming very difficult for a hacker. And you have time to react if one share is corrupted by a hacker. So the beauty of that is if one share is hacked, you still have the option to reconstruct your original data by the two left shares. And so this is and what we respond with that application is that it's easy to deploy because it's working in a classical computing environment, as we all know today, and there is no, ramp up of understanding the quantum technology because it's all classical. It's running on classical computers and classical network. And the second thing is you don't need to have a set of keys that you manage with your piece of data. As I don't know if there are any, people involved in the IT section of their companies, but one of the major, hassle, if I should say that, for IT managers is to handle all these keys related to your data, rotation, regeneration, maintenance of these keys, make sure they are protected. Here we don't need actually keys because we are based on shares, so it's keyless application, and you don't need to worry about all these keys. And the last thing that I wanted to stretch here is what Katanya mentioned, the store now and break later is your data. If you apply our solution, meaning that you already have your data that are protected now, and if people are trying to steal your data and store your data somewhere, they will have only some part of your data, some shares, and they won't be able to reconstruct your data. So by applying this solution, you are already preventing the store now, break it later. The last, well, here is an example of, different use cases that you could apply with this PQC solution. So just maybe highlight some of them very quickly. For example, in the medical industry, health industry, where the patient data are shared between, different hospitals and different facilities. Here, you can make sure that by applying our solution, the data that are recorded are really, really really secure. In finance, in the financial industry, you want to maintain the confidentiality and integrity of your financial transaction and make sure nobody has access to bank or finance account or personal account with personal data. Again, you can use our application to make sure it's fully secured and the harvest now, decrypt later won't work. These are a typical example. The last two applications that I want just to quickly present here is regarding data computation. So what we have developed is actually two line of product. That one line of product is a PQC algorithm that apply to actually AI, artificial intelligence. As Katanya mentioned, artificial intelligence is great. I mean, it solves a lot of your questions, but it keeps your data, it stores your data, it actually pumps all the data from the world. So and right now, like if you go to ChatGPT, all the data are unclear. Let's be honest between ourselves. All our data, our day-to-day data today are somehow in the hands of ChatGPT, and they can do pretty much everything that they want to do with this data. We don't know. Maybe they are very honest, maybe they are not. We don't know. Anyway, so what we came up with, and we're working with some AI companies, is there is a way, and especially in federated learning, it's a very specific type of artificial intelligence where actually the data of you as a user are kept in your site, and what you actually send to the server that computes this the data in order to provide you with an answer, they are only using what we call gradients. So meaning they are able to use not the original data, but just like the difference of what their system has been trained between what you provide to them. And there is like, something that they are able to calculate what we call the gradient. Anyway, I won't go into much detail in that, but this is what we call federated learning. What we have come up with some of the companies is um, they actually um, have to have two different servers, and then we apply the same kind of what I presented to you as CASMAT, that is the shares. So basically, we split your data as a user into different shares, like two shares at the minimum, if they have two servers, and then we send part of this data, I mean, share one to the first server, share to the second server, and the server are able to do their aggregation to be able to compute what they want and to be able to give you an answer. And then on your side, you get their answers from computer one and computer two. And then you are the one aggregating these two shares and having the answer. So by doing that, it's kind of going into a kind of a blind AI, meaning the AI are still powerful, they are still able to compute and provide you answers, but they have no knowledge of your data. So this is one thing that we're working on, and we have, a solution for. And the last thing is what we call Q-Enclave, and I just wanted to highlight that because it's actually the blind quantum computing. So as Katanya mentioned, here on the right side we have our quantum computers, and as Katanya mentioned, it's not a quantum computer; it's actually a refrigerator. Anyway, it's the way that most people are using this server icon. And here, what we do, we are able to actually connect classical computers to the quantum computers. And in the middle, we have this box that is, VeriQloud box that is able to translate your classical data and algorithm that you want this supercomputer to compute for you because it's complex, into turn this classical algorithm data into quantum data, encrypt them in a way that the quantum computers will be able to compute, but it will compute on encrypted data. So it won't have any knowledge of your algorithm, of your data, and then you as the end users are able to get what you expect, but your data are fully protected. And this is what we call blind quantum computing. We have been doing these experiments through the world in Europe, in Asia, and now we are kind of doing it here in North America, in Canada. Pretty exciting. And I guess that's it. So thanks for listening to me, and I hope it was useful. And if you have any questions, whatever, feel free to ask.
Hi, Dieter. We do have one question here from Mark Horseman. He was asking if what you were speaking about was like shotgunning your data, but only you can put the bullet back together in the end. I'm not sure if that makes sense to you.
It was when you were talking about, I think, Kismet, or when you take one share and send it to Google, one share of your data.
Yeah.
Mhm.
Okay, so I'm not sure I understand completely the question. So what was the question again?
Can I unmute? Is that easier?
Absolutely.
Um, so when you were describing shares, I was trying to put together an analogy to understand that. Is it kind of like just blowing out a shotgun or a bleh of data, but only one person can put all of those tiny bits back together to make a whole at the end?
Right, exactly. So basically, the way it works is our architecture in terms of software, we have what we call a proxy that is the main application. And the main application actually has the algorithm that is based on mathematical different protocols that actually take your original data and split it into shares. And the number of shares that is ending up with is based on your own configuration. So the more shares you want to generate from one piece of data, the more secure it is, obviously, right?
Oh, yes, yes, yes.
So you could define in our proxy, I mean, our main application, when I want this very sensitive data to be able to be split into 10 shares. And then you let our system doing it. So our system is the only one capable of, generating these shares and throwing them in different location where you have configured that in our systems. So you say, I want these first two shares into this location, these two in another location, this one in that location, the fifth, whatever. But then there is, another piece of our software that are called the nodes that are, kind of sitting on the different clouds where the shares are, and they're constantly talking to our main application that is the proxy. And so when you as a user say, oh, hey, I want to have my data back and original data, you just go into our system and say, hey, can you give me my piece, my original data? So the system will actually converse between their nodes and the main application, pull back the shares, and will reconstruct your original data. So yeah, this is the way it works. I hope I answer your question.
Thank you for that.
Yep, thumbs
Um,
up.
yeah. Okay, we have a few more questions here. Should I keep going?
Yeah, if anyone has a hard stop at the top of the hour, thank you very much for joining us. But we're going to keep going and we're not going to stop at the top of the hour. So there's lots of questions in the chat. The speakers are good to keep going. So yeah, I think just let's take a couple more questions for a few
Yeah.
more minutes. Yeah.
Yeah, and just to reassure, because I am getting some messages here, you will get the recording for today's webinar as well. So if you
That's
have to
right.
leave, that's okay. Then you can continue with what will be sent to you afterwards. So Dieter, I have another question here from Blaine. He's asking, with quantum cybersecurity, where do you see human risk fitting in? Does the human layer become more or less of a vulnerability?
The human layer, meaning, um, not sure I understand
Probably,
the human
I
layer.
think he means
Sorry,
probably just as a factor.
let me just explain that a little bit more. Human layer meaning, right now most cyber attacks is at the human layer meaning someone gives up their credentials, someone's socially engineered, someone is shows your password to someone. That's around 80% of social of cyber attacks are human error. So from a human
Right.
risk perspective, considering quantum is still a technical response in the cybersecurity realm, where do you see a human layer of those vulnerabilities fitting in?
Right, right. That's a very good question, actually. And I think, at the end of the day, there is a user that is, has the original data that are in clear because he wants to do something with it. So if this end user does not really pay any attention and, show their password, their original data to somebody else, then here we go, right? So we cannot really avoid that. What we can avoid is definitely, once the data are stored or in transit, like in a network or in computation. But if somebody is like the human risk will still be there, I think. I don't think it will secure more the human risk.
Okay, thank you. There's a few questions here. I might not be able to get through all of them, Mohammed, but one question from Mohammed is, what is the primary function of Conclave, I think, in the quantum computing ecosystem?
Yeah, so the primary function is to be able to secure the data that a client wants a server like a super quantum computers to work on. So as you do today, right, with AI, although we say AI is not quantum, but you want you have a question and you say, "Hey, ChatGPT, can you answer my questions?" So what happens? You are the clients, and AI behind has a multiple superpower computers that is ChatGPT, and they are computing, what you have thrown to them, and they come back with an answer. So what we're doing here with Qubo Cloud is we make sure that your piece of data that you throw to ChatGPT can still give you an answer, but it will have no clue at all of what your data are because it will be computing your data that are still encrypted. And we have a way to make sure that it is able to compute and give you what you expect in terms of results, even if all the data are encrypted and the algorithm that you throw to them are encrypted. So this is what we are trying to do with Qubo Cloud.
All right, and there's, I think, a follow-up, a little bit more technical or in-depth question. What cryptographic protocols does QAnclave use to verify the integrity of the execution environment on the quantum computer side?
Okay, it's basically one of the first blind quantum computing protocol that Elam Kashefi developed. So if what I can do, I mean, if this person is interested, I can throw some of the publication that are behind that protocol if that person is interested.
Yeah, I think that's a great idea. And there's a few more questions that we might not be able to get to right now in the chat. So if you want to answer Didier just in the chat, that would be great. And then maybe towards the end, when we stop the recording, we open the floor. If there's anything outstanding that we could then address when we're around. Sound good?
That's great.
Great. Well, thank you very much. That was a fantastic presentation. And I will share my screen again and get some music going. It's always nice to give a little music break to transition our minds from one topic to another, especially when we're talking about quantum physics. So, like I said, now we're going to go through some use cases, a few real demonstrations of quantum communication, and then we will have our second speaker, Erik from Photonics Foundry. So, please continue to ask questions in the chat. It's looking great. We love all the questions, so let's keep it going. So what is quantum entanglement distribution? So this is actually one of the main workhorses of the quantum internet, quantum communication, things like this. So distributing quantum entanglement sounds just like is exactly as it sounds. So you see in this cartoon, you can have a server, a central server at the middle, and now you're sending out beams of light to your users, and that's sharing the entangled photons between the server and the user. So you're literally distributing entangled photons. Why would you want to do this? Well, the quantum internet needs to have that ability, right? So if we want to connect quantum computers, sensors, communication devices, we need to have a network that can distribute either entanglement or at the very least single photons. Also, you can have secure quantum communication using untrusted parties. So you can have like a blind quantum computer or a blind server that's distributing entangled photons to different parties who can then use those entangled photons for their own encryption, for their own computation. And the server in the middle can be untrusted, which means they could be compromised and it won't compromise you or your data or what you're trying to do. Also, if you want to connect distant quantum sensors to make a quantum sensor network, then you need to be able to distribute entanglement. You can do enhanced timing accuracy this way, also sharing synchronization. There's tons of applications that require synchronization. And so, yeah, that's another definite advantage. So quantum repeaters and teleportation. So I haven't really talked about teleportation yet, but it's very similar to the entanglement swapping. These are operations that quantum memories and quantum repeaters use to pass on the information. And so literally, quantum repeaters won't work if we can't do entanglement distribution. And then we also need, like I said, quantum repeaters to be able to extend the entanglement between distant quantum nodes, and this is operating via entanglement swapping. So let's talk about some real use cases of quantum networks now. There are numerous quantum testbeds that have been emerging in several countries, including North America, China, Europe, etc. There's been a recent demonstration of entanglement distribution on a quantum network at the telecom wavelength, so 1550 nanometers, the fiber optic network color that we all use now for the internet. And so they've demonstrated entanglement distribution on a real-world optical fiber infrastructure in the US, in New York. So QConnect's Gotham Q quantum testbed is a fully automated system that's capable of distributing polarization entangled photons over these buried optical fibers. The overall network length was 34 kilometers. They were able to achieve end-to-end pair rates of 500,000 pairs a second, and the entanglement fidelity, so how good did the entanglement keep over the network, 100% would be perfect. They achieved 99% fidelity, which is just amazing. And it was over a 15-day period of continuous distribution. So this wasn't just a one and done. They did this over 2 weeks, and the network uptime was 99.84%, so almost all the time. You can see a cartoon here. If you want more information, all of my slides, which again, because you're attending live, you will get a copy of my presentation. You can see there's archives, or the publication will be on the slide, so you can look up more information. But if we have a network of people that are distributed further than 500 kilometers, that magic number of what we can send within fiber, then we want to go to space. And so having ground-to-space quantum links is very, very advantageous. What would you need to do such a quantum link? So we need a ground station. You can see in this cartoon, it basically looks like an observatory. It's just like a telescope that we use now to collect light from the stars, except now you can use the light, the telescope, to send light up to a satellite, so an uplink configuration, or you can have your quantum source on satellite, and then it's coming down to the ground station, and it's a downlink configuration. There's advantages and disadvantages to all these different protocols, ways you can send the light, if it's an uplink or downlink. The best choice depends on what your situation is for your link, the link conditions, and what kind of quantum devices you're using. And then another thing I want to mention is high altitude platforms. And so it's really hard right now to link to a satellite, to do a quantum link, because obviously the satellite's moving very quickly overhead. We only have a few minutes to link. Weather is a big issue. Quantum links don't work in clouds right now. So like our everyday internet, we can have it all 24 hours a day, 7 days a week, doesn't matter the weather. Quantum links are a little bit different right now. They're more sensitive. And so you can have a high altitude platform that is between the ground and the satellite. So it's at, say, 20 kilometers at height, so that you're overcoming a lot of the atmosphere, overcoming a lot of the weather, and then you have a longer link time to your satellite because of the line of sight. So there's a lot of advantages to incorporating high altitude platforms, quantum drones, and also low altitude platforms into these quantum satellite networks. And there's a lot of work going into this right now. Like I said before, you get longer link times. The high speed of the satellite that's rotating over the Earth means that the ground station only has approximately 6 minutes at best to link. Whereas a HAP to satellite is significantly longer. It could be hours, depending, well, maybe not hours, but it can be a lot longer than 6 minutes, that's for sure. And then avoiding the weather, so mitigating clouds, the weather, preventing the ground station from linking. So a HAP could literally be above the clouds. And this also helps avoid the turbulence. So the reason why, you know, when you look up at the stars and the stars are twinkling, it's because the light is traveling through the atmosphere and it's breaking up and it's causing these turbulence effects. And so the same thing happens to our laser light, and that can cause our signal to be remember how loss and noise are bad for quantum signals. So turbulence is like a form of loss and noise. And so if you are getting a disturbed quantum signal before it goes up to your satellite, that can be a problem. So if you can overcome a lot of that atmosphere and then send it from the HAP to satellite, there's a lot of improvements. And this might, again, sound like science fiction, but it's really not. The level of miniaturization has been progressing, and now there's quantum devices being installed on drones and HAPs. And there's a lot of applications for these types of satellite networks. For example, you could improve our current positioning systems. So traditional global navigation satellite systems, or GNSSs, can have errors for accuracy for your position in a range of 10 to 15 meters. And that can be very unacceptable for some applications. And so you could use, for example, a quantum satellite-based network, having your quantum 2.0 atomic clock, so an even more accurate atomic clock than what we have now. And because you're networking these satellites together, you would have improved accuracy, synchronization, and but you, again, need entanglement distribution over the network to do that. And another real-world application of quantum technologies, this was a demonstration done in China. You've got the Mishia satellite in this case talking to 2 ground stations, and then one of the ground stations near Beijing is also connected to a fiber optic network. And so the fiber optic network is roughly 2,500 kilometers. And so this total link connection is roughly 4,600 kilometers. And so you can see that each red arrow here, it has a multi-user network at the city. And so this would be what we're talking about for the future for a quantum network. You would need your local metropolitan networks to share the data with your users. Then you would have your connections between those networks, and then to connect networks to networks that are too far to send directly than you do via satellite. And a very recent demonstration, another mission from China. So this was a quantum microsatellite that was launched in 2022. And it has, they also created a portable ground station. And so not only did they reduce the weight and size of the satellite compared to the previous mission, but they also reduced the weight and size of the ground station. So it's really important in order to just deploy these quantum networks near urban environments, to be able to have like a portable ground station that you can set up within the day or within a few hours, not requiring a lot of infrastructure. And that's basically what they were able to do. And so they demonstrated a space to ground. So this was a downlink. So the source was on the satellite and the detectors are on the ground measuring the light. And so they were able to get a maximum secure key rate of almost 1 megabits per satellite pass. So remember, they'll only be able to link while the satellite is in view of the ground station. And so these were also polarization encoded photons, but this was without entanglement. This is just with single photons. So as I said before, you don't have to have entanglement to have secure communication. You can use single photons as well. Another really cool aspect of this mission was the fact that it was a multiplexed bidirectional satellite to ground optical communication. What do I mean? So every satellite right now has to talk to a ground station via RF and microwave signals. So that's not quantum, that's classical RF. But if you can use laser comms, and so that's the optical version of that RF signal, you have a much higher bandwidth you can send more data and things like this. And so in their satellite, they combined both a quantum source and a classical light source to do their laser comms, so that they were not relying on the traditional RF microwave communication link. And so this allowed them to do real-time communication, because if anyone's ever joined one of my seminars before, I always talk about how QKD, even if you have entangled photons, it doesn't mean you can have communication faster than the speed of light. There's always a classical phone call that has to go with every protocol. And so this classical phone call going at the speed of light is this laser comm signal. So even when the satellite has done its quantum pass and you have your single photons collected and everything, there's still traditional classical data. There's communication between Alice and Bob that has to happen. If that has to happen in real time, that was a big limitation before. So you'd have to store up your photons, store up the data, wait for the passes, wait for the RF signals to come. It could take 3 to 4 downloads depending on the data rates and things like this. Whereas in this mission, they were able to do it all in one single pass. And if that wasn't enough, they used the secret key to actually create an encrypted one-time pad encryption to encode an image and then share it between China and a ground station in South Africa. And the total distance was almost 13,000 kilometers. All right. I see there's lots of things happening in the chat, but I'm not sure if any of the questions are for me. But that's the end of my talk. Oh, Reiner has a hand up. Please.
Yeah, thanks, Katanya. This has been very helpful, the overview. How does Canada's satellite, KeySat, that I know you're intimately familiar with, stack up against the satellites China has launched in terms of capabilities? Is it equivalent, or are we playing catch up, for example?
Great question. So there's a lot of different aspects to these satellite missions. And like I said, do you do an uplink or a downlink? And so with the China missions, they've been doing downlinks because it's a little bit easier to get the signals if they travel mainly through outer space first for the first like the satellite's usually at 500 kilometers above the ground. So for the first 480 kilometers, you've got vacuum, and so your photons don't get messed up by the turbulence, and it's only at the very, very end where it gets messy. Whereas if we do an uplink, we have to go through the messy atmosphere first. So by the time it gets up to the satellite, it's very messy. And so that's why primarily quantum missions have been downlinks. Whereas the KeySat mission, the quantum encryption and science satellite launching from Canada, it will be primarily an uplink mission. So you'd say, why would you want to do that? You just told me how bad the atmosphere is. But now, if you have your uplink configuration, so anything that you launch on the satellite is frozen in design. It's not like you can capture your satellite and switch out your detectors or your sources and make them better. So anything on the satellite is fixed. On the ground, if we have an uplink configuration, we can swap in different quantum sources. As the engineering improves, we can swap in better sources. And so as long as the light that we're sending up to the satellite is within the passband of 780 to 795 nanometers, so the red passband, the light will be received by KeySat. And so we'll be able to test on the ground what sources can make the links better to overcome that turbulence. Also, adaptive optics. So we have the ability on the ground to do a lot of adaptive optics to basically overcome the turbulence and to compensate for it. And so all of that is part of the mission. So I would say, although China has launched already satellites and they have already demonstrated a lot of the big milestones, like showing entanglement distribution across very vast distances, things like this, they haven't done everything, and there's always more to do.
Thank you.
Great question.
Yeah, there's a question here from Sunil. I think it's for you. Is it possible to make quantum links on cloud? If yes, how is it possible? And if no, what makes the problem, or what makes the problem or difficult?
Like cloud computing, like on the cloud like that?
Sunil, if you can verify what you're asking.
Yeah.
Yes, cloud computing.
Right. Okay. So with cloud computing, it's still classical. And I think it's probably more of a question for Didier. But I don't know how we could merge that quantum links on cloud. So not sure. Didier, I don't know if you have more.
Can you just ask, I mean, what's the question again? Sorry.
Sorry. Is it possible to make quantum links on cloud? So the cloud computing, or and if yes, how is it possible? And if no, what makes the problem difficult?
So if I understand correctly, is because I mean, one answer is clouds. Behind the clouds you have supercomputers. That could be high powerful classical computer, HPC computers, but they could also be quantum computers. And what we see already for mainly experimental application right now is that Google is providing via the cloud the quantum computers as well. So we are in a paradigm where actually clouds, like public clouds, like Google, AWS, already providing quantum computers, but mainly for experimental. So we are in these architectures of public clouds that offers actually quantum computation. But right now, the current situation is that you throw your data, in clear to this quantum computers, and yeah, so basically AWS or Google have access to. But we could actually try to work with them and implement a first version of the blind quantum computing. And to be honest, we have been, approached and kind of starting some work in this area with these super cloud companies.
Nice.
Thank you. Mark, I see your hand up. Feel free to unmute your mic.
Thanks. And my apologies for asking a noob question here. I really don't I don't understand, but I do, but I don't. Just the nature of quantum entanglement. So we're sending a signal to create a handshake to understand the entanglement of two particles. And then once they're entangled, we can affect one and it'll affect the other, kind of like the three-body problem. Sci-fi where you got the sapons and they're talking to each other, but it doesn't really work that way, does it? Like you can't, how does it function? Like you affect one particle, but you can't really observe the particle because you don't know in real time if the other one's been affected yet. Am I making any sense? I'm just very confused.
I know, I get it. And if this was more of a technical webinar, I would have had a thing about entanglement. But on a high level, I understand what you're saying. You've almost got it. You've almost got it. There's a signal, a correlation, something that's going between these two particles, and it's like they're communicating, and it's like that communication is happening instantaneously. So like if I create two entangled photons, two particles of light that are entangled, remember I was talking about polarization entangled photons, so that means like their polarization degrees of freedom are the things that are correlated, are entangled. So I could have a polarization entangled state where one photon, if I measure it to be horizontally polarized, then automatically the other photon will be vertically polarized, and vice versa. If I measure one to be horizontal, then the other one is vertical. So you can have entangled states where that is true, and until you measure one of the photons, the entangled pair is in this weird combination state, superposition state of the two polarization states. And you can't separate them. If you know about linear algebra and mathematics and stuff, when you take something, if you can make it separate, if you can take an equation and make it into two parts, that those parts to multiply it together will give you the answer, then it's separable. But in an entangled state, you can't do that. You can't mathematically describe one of the particles without describing the other particle too. And so that's very, very special. And so until you measure it, you don't know what the polarization state is of either particle. It's half of one and half of the other. horizontal and vertical. But then as soon as you do a measurement, the quantum state of the other particle that wasn't measured gets affected. So that's where it's like instantaneous transmission of information, which makes no sense. But this holds. We have done experiments now with satellites showing entanglement distribution over 1,000 kilometers. So that is a physically large enough distance that the speed of light is measurable to be slow compared to instantaneous reaction of the entanglement, and you can see that. So even though you take a measurement and you collapse the quantum state and it happens instantaneously, it doesn't mean that the entanglement means faster than light communication, because like I said, you still have to have this classical handshake, this physical classical phone call to finish the protocol. So even though you've done the measurement, you've collapsed the state, you have your two photons, they're each in their own polarization state now, they're not in a superposition state anymore, there's still a part of the information missing, and you have to have that classical phone call to finish it off. And I go through all of that in my courses if you ever want to know more. Great questions.
Right.
Oh, I'll take one more, and
one
then
more?
we
Okay.
should go on to Erik. Yeah.
Sure.
And then I'll reply in chat. Yeah.
Sounds good. There are two questions from Mohammed, so I'll ask the first one from him. Why not make a satellite with a long model on the quantum model and no one makes it? It should be possible for models and satellites and signals can also be directed to rain or detect earthquakes related to reduction in radiation or frequency ground systems in situations in low positions and positions above lowlands, highlands. Do you understand what they're asking?
I'm not sure what a long model on the quantum model means. Make a satellite with a long model on the quantum model. I'm not quite sure. My apologies. If you want to unmute and clarify, you're welcome to, or just write some more in the chat. But yeah, I'm not sure. But I can just let you know now, quantum sensors can be used to detect earthquakes, which is pretty cool. Like I said, like fiber optic cables are really good at detecting vibration, and we can use that to our advantage. So just as a side note, you can make a really precise interferometer that will measure vibrations in the earth and be able to measure earthquakes.
Thank you.
All right, I'm going to play a little music and bring on our second speaker. And let's pretend we don't know who it is again. Get ready for our next guest speaker, another quantum tech founder, Erik. Welcome, Erik. He received a diploma in precision engineering, also a PhD in optoelectronics systems integration. Erik works at the Fraunhofer Institute for Applied Optics and Precision Engineering in Jena, Germany, and is now the head of the department of the I didn't practice this one, mechatronical components and systems. And he's also the co-founder of Quantum Optics, which is a company in Sweden, and also Photonics Foundry, where he also serves for design and business development of photonic assembly services. Welcome, welcome, welcome. I'm going to stop sharing my screen. And Erik, if you'd like to bring up your slides, and we'll get you onto our virtual stage.
Okay, thank you, Katanya. I hope you can see my slide now.
Yes, it is. And we will monitor the chat, and we'll just save questions till the end to let you present. So thank you.
Okay, great. Okay, so second talk of the webinar, Photonics Foundry company as a quantum hardware enabler. So you have heard from Didier of VeriQloud before that they are a solution developer that makes use of hardware and software to provide a solution based on quantum technology, and Photonics Foundry is a hardware company. So we are a little bit more upfront in the value chain of quantum technologies, as we are providing quantum hardware, in particular quantum hardware that is based on photons as the particles that carry a certain quantum information. As the workshop is for executives, I thought it would be a good idea to make sure that quantum is not only fancy and nice, but that also people projecting a very interesting business outcast for quantum technologies. I dig that out for photons as the particle that carry quantum information. You can do the similar exercise for other particles like atoms or ions. But you see that even for photons only, detect the quantum information, there is quite a big market segment to be forecasted from the company Yole. And that is exactly the reason why people say in these different fields, in communication, in computing, in sensing, they say they see such a lot of new applications that go beyond what is possible at the moment with classical technologies. So you have heard already about communication based on quantum technologies that make physically secure links. The space people are interested in that, but of course also people on the ground. We have also heard about the quantum computing and what is eventually possible in different fields of applications using a quantum computer, and even some crazy guys are thinking about to put a quantum computer into space. So this is also a discussion that is going on at the moment. Quantum computers not only on the ground, but also in space. And last but not least, also imaging and sensing here in space, but also on the ground, do see a lot of interesting applications for quantum technologies. So high accurate accelerometers, gravimetry instruments, magnetic field detection. People even think about putting quantum sensors into the car for very high resolution collision detection and so on. So just to make sure, yes, there is also a big business potential for quantum technology, and that should be an interesting message to executives from all over the place. Katanya already talked about the quantum 2.0 revolution. And the slide is eventually illustrating what the quantum 2.0 revolution is in principle about. Quantum technologies want and have to leave the laboratory and go into real environment. So you see on the very left, this is what quantum physicists have been doing for more than a few decades now, developing functionality of quantum systems in the laboratory. But the quantum 2 revolution is about bringing these functions into a real environment. You see in the midst the rocket that brings quantum satellite into space, but you also see on the right that quantum technologies like secure quantum processors, things like that, eventually also go into consumer products on the ground. And taking photons as the example of particles that carry quantum technologies, there is the first challenge to develop the systems in a way that they can really be brought into the field, but the same is relevant also for other particles like atoms or ions or spins. And the actual challenge illustrated is that people really have to think, where is your product in this evolution roadmap here shown on behalf of the photonics evolution roadmap. So we have here, yes, quantum physicists start in the laboratory, but in order to, where they do a proof of principle of what they want to do with quantum, they even then think about so-called elegant breadboards where quantum physicists already think, yes, this can maybe go to space. I, as an engineer, say there is still a way to go to space. Since the next evolution step is then typically that we design such breadboard systems from the laboratory in compact bulk optics to send them in real environments. But when we want to do business with quantum systems, we really have to talk about scalability, not manufacturing one compact bulk optics that does a quantum experiment, but manufacture many in an automated production so that you can really deploy that as a product into the field. For instance, small modules that are comparable to telecom lasers, but that provide quantum technologies. Even putting the quantum technology, sorry, it's behind the previous picture, even putting quantum technologies onto chips like microelectronics chips. And this really can be compared to the evolution of microelectronics systems. Microelectronic systems also started with a proof of principle and single transistors, and then IBM people built a computer out of that, and they thought maybe 3 computers in the world are needed to do some calculations using such a thing. And nowadays, microelectronics things are integrated onto the chip, and quantum systems are expected and are required to go the same way. But when we look at photons and photonic systems for quantum, then people that want to do this job, they face quite a few further challenges. We call it the valley of death for launching a product in the field of quantum photonics. And that, by the way, is not only relevant for quantum photonics, but is also relevant for photonics in general. So we talk about a long development time versus a short product time. We talk about extensive production infrastructure where you need highly skilled people. And of course, nowadays, we also have to talk about geopolitical challenges, for instance, regarding the materials that we want to use for this hardware, and also leaking of IP and so on. So you see on the right 2 more or less sophisticated or complex photonic devices that can be part of a quantum photonic system that eventually illustrates some of these challenges. And that is actually what the Photonics Foundry as a company is providing. We, as a company, provide a service for people that have a nice idea for a product in the field of quantum photonics technology, all at each eventually possible entry point of the product state. So it might be that people have only a design. We tell the people you have to modify, optimize your design so that you can really do prototypes or a real product in an automated assembly out of it. We do the prototyping for such people that have a product idea. We even scale up the production for these people to small and medium volumes, even large volumes. Some of the product people want to stay fabless. They say, I need somebody that manufactures my product. This is also what we can serve for. But we can also transfer the hardware and the know-how to people that in the end then want to manufacture their own quantum photonics product. So this is the service that this company provides. And this is exactly a service for people that are new in the field of quantum, that eventually have a nice idea about a quantum photonic product, a quantum hardware photonic product, and that look for partners that can realize this product for them. The company itself, you see the 3 co-founders here, and I can tell that at least I myself brought in the quantum know-how into the company, as in my institute, Fraunhofer IOF, I'm dealing with quantum hardware as an engineer for something like 15 years now. So I really started with that at the very beginning of the quantum second 2.0 revolution. The company is situated in the small town of Bremen in Germany. So if you're familiar with Europe and Germany, you will see that Bremen is in the northwest of Germany, where we sit in a very new facility with clean rooms and very dedicated photonics, automated photonics assembly infrastructure that allows us to manufacture photonic quantum product for our customers. And by that, the final message is quantum is nice, but as long as quantum stays like you see it on the left side, this is what Chinese scientists did when providing the first functional principle of a photonic quantum computer on the laboratory breadboard. So functional demonstration of a photonic quantum computer. You can imagine that this is a nice functional demonstrator, and you can also imagine that the company Tor Labs probably made a fortune out of this setup. But this is, of course, something that will never go into a real product. A real product you rather see on the right, where something is put onto a chip comparable to a microelectronics chip and can be manufactured and packaged in a scalable way. And by that, I thank you for attention, and of course, I'm also open for questions.
Wonderful. Thank you very much, Erik.
All right, let me see here. There are a number of questions here, Erik. Give me 1 second here. There's a question asking about dark matter. Although we cannot see it, we know dark matter exists because of its gravitational effects. From a quantum perspective, is dark matter composed of hypothetical particles like axions or weakly interacting massive particles?
Oh,
I'm not sure if you're a dark matter expert.
No, I'm not. I would briefly like to emphasize one thing. Quantum is realized by physicists, and the physicists, maybe like Katanya, can also try to answer this question. I myself am an engineer. I let the quantum physicists say, I have this setup, prepare me the setup in a way that I can bring it to the field. So I'm the engineer that has to understand a little bit, or most of the quantum things, but has that will bring in engineering heritage to build the systems in a way that they can brought onto the field. So the question is really for not me as an engineer, but for a quantum physicist who would like to volunteer about that.
Yeah, maybe we'll hold these quantum
Yeah, maybe.
dark matter questions to the end.
Well, let's try Sunil's question here. What approaches are you using, with the quantum error correction on qubits of the photonic quantum computer?
Can you say the...
I think it might have been the picture you showed of the photonic quantum computer from Pan's group, Jamie Pan. I think the question is specifically about the. I'm not sure if we would know based off of the experimental diagram. Erik, correct?
I probably don't really know this detail of the Pan's setup.
I'm not either familiar. Let's try the next one.
Marco's got a question here. What would you say are the challenges of scaling the photonic devices?
Yeah, this is what I try to emphasize really in my talk. When you talk about technology, you really have to take this potential scalability into account. Katanya showed in the very beginning this picture of the quantum computer, where we said this is not a quantum computer, it's only the fridge for the quantum computer. and the chip that needs to be cooled down to 0 Kelvin is in the very bottom of the chip. So if people cannot provide scalable cooling technologies for cooling things down to the 0 Kelvin range, then such a computer will always stay a kind of singular piece that maybe an institute or a governmental institute can install in their laboratories, but it will not be a scalable quantum computer that eventually somebody wants to integrate into a smartphone or something like that. So you can always compare it with microelectronics. Microelectronics in the end was scalable only when people brought it to the chip. So this is the ultimate goal for scalability. If you have small microphotonic modules like that, this eventually is a predecessor of scalability, since even now laser sources in telecom racks or things like that are really manufactured at high volume. So there you could also argue that this is also already a scalable technology, but it's really about the scalability of manufacturing and integration technologies that is the bottleneck for the applications of quantum technologies.
Yeah, that's an excellent point. And trying to put cryogenics in space is really hard. But there are devices that work at, quote, room temperature or can be reached with a TEC, a thermoelectric transducer or coupler. Do you use TECs in your photonic devices sometimes?
Good question. When people say photons as the carrier of quantum information are a good thing since they can be used at room temperature. So people always say the photonic quantum computer is a nice thing. It can work at room temperature. It is only halfway true, since to detect the photon, you again need a cryogenic cooled detector. So this makes the story only halfway true. But even raising the required temperature from 0 Kelvin to something like 4 Kelvin, or even some minus 20 to 40 degrees that you can achieve with a classical attack helps already a lot. Even the small step from 0 Kelvin to 4 Kelvin or even 70 Kelvin, something like that, this changes the cooling technologies and already helps a lot in scalability.
Definitely. Yeah, it makes a big difference. And I also see Reiner has a hand up. Would you like to ask a question?
Thank you, Katanya, and thank you, Erik. Like yourself, I'm an engineer, and my question is with respect to the substrates that are often required to build these devices at scale. As you know well, traditional integrated circuits are on a silicon substrate, but photonic integrated circuits often perform better on different substrates, gallium arsenide or otherwise.
Yes.
How is the challenge of integrating or combining those substrates? How are you overcoming that at your foundry? Or are you just separating them and then basically using waveguides or pigtails to interconnect a silicon substrate, for example, with a gallium arsenide substrate? Of devices built on those substrates.
This is a highly relevant question. Since, let's say, compared with microelectronics, maybe you can say in microelectronics everything can be integrated in CMOS technology, more or less. You are completely right, Rainer. In photonics, different material platforms come into play. Silicon nitride, indium phosphide 3,5 materials, all of them have different performance opportunities, but none of them has a sum of all the functionalities that you need. So there's one way that you connect these different PIC platforms by fibers, which poses then the challenge not to use too many of these precious photons at the interface between the chip and the fiber, so ultra low loss fiber coupling. is the hot topic that arises here and that Photonics Foundry is also covering. And the second approach is like the microelectronics people also do a little bit. They stack chips onto each other and make electrical interconnections between the chips. And this is also something that photonic guys do. They create chips with different functionality, and on the waveguides on the chips, they create evanescent couplers.
And you can have VCSELs on the chips to stack vertically then too, is that
or
what you
that,
do?
or you even have vertical light emitters.
Okay.
And there are many research activities going on to stack chips onto each other, of course, then providing light interconnections between the chip that, again, of course, should not lose too many photons and shall provide high-speed interaction between the chips. But this is the second approach where technologies like submicron pick and place or microtransfer printing of one chip onto the other are currently investigated.
I like that vertical stacking one. I hadn't thought of that. Thank you.
Yes.
Wonderful. Great questions. Excellent. I don't see any other hands or anything in the chat. So I'm going to thank you again, Erik, and I'm going to go back to sharing the screen, and we'll just wrap up before we stop the recording. And so we can open the floor in just a second. All right, and thank you to both speakers. That was fantastic. And thank you to all of you for attending this wonderful webinar. If you'd like to learn more, please check out the Qubo website, connect with me on LinkedIn, and I hope to see you at another webinar or course soon. And you'll be the first to hear, we have another webinar coming. On June 18th, I will be presenting Quantum Sensing for Executives, the advantages of quantum LiDAR and PNT devices. PNT stands for Positioning, Navigation, and Timing. So if you want to register for this next webinar, it will be, again, in 1 month. You can go to the website. It'll be non-technical, presenting the key distinctions between quantum and classical sensing, as well as real-world demonstrations of these quantum sensors. Quantum sensors have a reduced size, weight, and power. They're swap, making them very attractive for the space industry, as we were hearing from Erik. And also being able to provide navigational information in GPS-denied environments. So that is a really, really big plus for these types of sensors. So I hope to see you again. All right, thank you so much. And big round of applause to everyone.